So let's bring this new notation into how we talk about velocity and instantaneous rate of change and things like that. So the instantaneous rate of change of a function f of x at a value a is its derivative f prime of a. So this is just stating again that this derivative is related to instantaneous rate of change, is also related to that slope of the tangent line. So those three terms are interchangeable. So let's say we have a function that's describing the position of an object. So s of t, so s is describing the position, which we'll be describing as a distance. And then t is going to be the amount of time that's passed. So what this function's doing is describing how far away an item is in relation to time. So if we want velocity, that is going to relate to the first derivative of that position function. So we would write that as s prime of t. And if you think of how slope is working and rate of change, if this is describing some distance and time, then if this is our rate of change, that's describing some distance per time. So like miles per hour, feet per second, things like that. Now acceleration is something we'll talk about more later on, but acceleration is going to come from the derivative of that velocity function. It's describing how our speed is changing. If we're accelerating, if we're going faster, that velocity is increasing. If we're slowing down, if we're putting the brakes on, that velocity is decreasing. So we're getting this kind of rate of change of a rate of change, which would be like a distance per time squared. And just to introduce some more notation that we'll talk about later on, if we're looking at the first derivative of a velocity, we would call this the second derivative of that position function. So we'll have a video on higher order derivatives where we can keep taking the derivative of a function, and this would be a case of a second derivative. So if we have a function describing position, we can find velocity with the first derivative, find acceleration with the second derivative. So let's take a look at how this works in some applications down here. So we have a rock is dropped from a height of 64 feet. Its height above ground at time t is given by this position function from t equals 0 to t equals 2. Find the object's instantaneous velocity 1 second after it's dropped. So what we're looking for here, and I'm going to write all sorts of notation just so that we see it, but it's like we want the velocity at 1 second, which is the same as the first derivative of our position function at x equals 1, or t equals 1 rather. So those notations are saying the same thing. This is the velocity at 1, and having the derivative of our position function at 1 is the same as having the velocity at 1. So what we're going to do here is take our limit as h approaches 0, and our function is s of t, so we're going to use s of, and we're looking at 1 plus h minus s of 1 all over h. And that'll calculate our first derivative at t equals 1 using our position function. Okay, so if I plug in 1 plus h, I'll have negative 16 times 1 plus h squared plus 64. So that's one part of my numerator, and then minus s of 1, which I'm going to use parentheses again. So minus 16 times 1 squared plus 64 all over h. And then we just start simplifying. So taking that limit as h approaches 0, we're going to have a negative 16, FOIL out the 1 plus h squared for a 1 plus 2h plus h squared, plus 64, minus 64 minus 16. Let's see what that ends up being. So we're subtracting a 48 over there. All over h. distribute the negative 16 through. So we'll have negative 16 minus 32h minus 16h squared. And then let's see, 64 minus 48 is a positive 16 all over h. And simplifying some more, the constant should cancel out, so negative 16 plus 16. And we could divide out an h, which will leave us with a negative 32 minus 16h. And now we can plug in h equals 0. So we're going to go negative 32 minus 16 times 0, which is negative 32. So our instantaneous velocity is negative 32. Let's get our units here. So we have feet and seconds. So it's going to be negative 32 feet per second. So getting that instantaneous velocity is using the derivative of that position function. Let's take a look at another example here. So we have a homeowner sets the thermostat so the temperature in the house begins to drop from 70 degrees Fahrenheit at 9 p.m., reaches a low of 60 degrees Fahrenheit during the night, and then rises back to 70 degrees Fahrenheit by 7 a.m. the next morning. Suppose that the temperature in the house is given by this function here. For 0 is less than or equal to 10 is less than or equal to t. So t between 0 and 10. Ooh, I stumbled on that one. Where t is the number of hours past 9 p.m. Find the instantaneous rate of change of the temperature at midnight. So if we're at 9 p.m., and that's going to be t equals 0, and we're looking 10, 11, 12, we're looking at 1, 2, we're going to be looking at t equals 3 here. So we want the instantaneous rate of change of the temperature. So I'm looking for t prime, capital T. This isn't great with the multiple t's here. So first derivative of t, and we're looking where time is 3. So we're going to look at the limit as h approaches 0 of t of 3 plus h minus t of 3 all over h. And using our function up above, this will look like 0.4 times 3 plus h squared minus 4 times 3 plus h plus 70. There's our first calculation, and then we're going to subtract t of 3, which will come from a calculation of 0.4 times 3 squared minus 4 times 3 plus 70 all over h. Okay, let's go to the next line here. So limit as h approaches 0, and we're going to have 0.4 times 9 plus 6h plus h squared minus, and we're going to distribute that negative 4, so a negative 12 minus 4h, and then we'll have a plus 70. And then we're subtracting, and I'm going to go ahead and plug all that into a calculator. So 0.4 times 9 minus 12 plus 70 is a 61.6. So we're subtracting a 61.6 there. All over h. Let's distribute that 0.4, so 0.4 times 9 for a 3.6. Plus 0.4 times 6 for a 2.4h plus 0.4h squared. Let's see, negative 12 plus 70 minus 61.6 is negative 3.6 plus 70 all over h. Now, something that you should be noticing is happening with these is that we have our constants, like this has a 3.6 and a negative 3.6. And actually, that's a great example. I just saw that plus 70, and I was going to say, these should be canceling out, and it's because I copied the wrong thing. So that plus 70 shouldn't be there. It should be a minus 4h. But that's a great sign of how it kind of double checks your work for you that the constant should disappear, because we're working with functions where h should be canceling out. So if you don't get that cancellation of h out because some constants are left over, it's likely an error in the algebra. So you'd want to go back and check things. Or in my case, double check that you wrote down the right piece and not going too fast. So that 3.6 minus 3.6 is perfect, because then with that, I can just focus on taking, let's see, we have a 2.4h minus 4, so that's leaving us with a negative 1.6. So I have 0.4h squared minus 1.6h, all being divided by h. Cancel out an h, so we're left with 0.4h minus 1.6. And with that, plugging in 0, we're left with a negative 1.6. So what does that tell us? If we put this in context, at midnight, the temperature is going down, or is decreasing, by 1.6 degrees Fahrenheit per hour. So T is each representing an hour after 9 p.m. So we get our rate of change at exactly midnight for how the temperature is changing.